Hello again, physicists. This video is going to take something that we've seen in class called momentum, mass in motion, and tie it into an additional idea called impulse. So to begin, we're going to go in our Wayback Machine and look at two formulas that we've seen already. The first being good old Newton's second law. A is equal to F net over m, where A is the acceleration of a system, F net is the net force acting on it, and m is the mass of that system. Our second equation also has to do with acceleration, and that is the fact that an acceleration is a change in velocity with respect to a change in time. Guess what? Two valid ways to express the same quantity of acceleration. So I can take these two equations and I can set them equal to each other. In fact, that is exactly what I will do. So if I set them equal to one another, that means that a net force divided by the mass of the system the net force is acting on will be equal to a change in velocity of the system over a certain change or passage of time. And that's what we would end up with. What I'm going to do is I'm just going to rearrange this a little bit. I'm going to do a tad bit of cross multiplication. That will give us something that looks like this. Where now we have the mass of the system times the change in velocity of the system being equal to the net force acting on the system multiplied by the amount of time that net force is acting for. And really, we saw in class that when you have mass and you have it moving, that is really momentum. And if my velocity is changing, that means that my momentum must be changing. So really, I can condense this part here into being a change in momentum. And when the momentum of a system changes, it'll be equal to whatever force is acting on it multiplied by how much time it is acting for. And this part right here is what we call impulse. And this equation, boop, 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 as I box it, this is how it appears on the AP equation table. So this is the equation that relates impulse to momentum. And if we want to put into words what an impulse is, it's basically a change in momentum that is caused by a net force. And it depends on really two things: how much force is being applied and for how long a time is that force being applied. I'm going to show you an example where we see how that factor of both time and force together will actually give you the same change in momentum. So here's the old egg thrown at tarp versus egg thrown at brick wall example. The way this works is we have two identical eggs of the same mass. I chose for each of them to have a mass of 0.1 kilograms or 100 grams. Both eggs will be thrown with the same velocity of 5 meters per second. And both are going to hit something. Egg number one will hit a brick wall and come to rest in a disgusting, splattering fashion. Egg number two, however, will hit a nice, cushiony tarp. That'll also bring it to rest, but prevent it from breaking. Let's do a little analysis here and compare how much each egg's momentum changed. Let's determine the change in momentum for the brick egg and the tarp egg. So the change in momentum for either egg will be the final momentum the egg has minus the initial momentum the egg has. For the brick egg, it is ultimately brought to rest, so that means its final momentum will be 0 kilogram meters per second. And we will subtract from that the initial momentum the egg has, which will be its mass times its initial velocity. which would give us 0.5 kilogram meters per second. So for the brick egg, the change in momentum was negative 0.5 kilograms meters per second. Excellent. Now let's do the same thing for the egg thrown at the tarp. Well, tarp egg also came to rest, so its final momentum is 0. And we will subtract from that its initial momentum, again, by taking mass times velocity. And lo and behold, the change in momentum for the tarp egg is identical to that of the brick egg. In other words, both eggs had the exact same change in momentum. What does that mean? At first blush, the conclusion would be that if both eggs had the same change in momentum, and impulse is a change in momentum, we can then say that both eggs experienced the same impulse. And that's true. But how they experienced the same impulse, that is different. Let me explain. If we look at the brick wall and what sort of impulse that egg experienced, well, the egg broke because the impulse it experienced was a large force that acted over a very short time. Whereas with the tarp, it was the same impulse that was felt from the brick wall, but here it is a small force that acts for a large amount of time. It's these two factors of force and time in combination that determine how much impulse an object will experience. So you can get the same impulse by having a large force and a small time versus a small force for a large time. And that's how they both had the same change in momentum, but one egg broke while the other one did not. It was specifically what manipulation of force and time occurred in order to make that impulse possible. This is similar to how you can have two objects with the same momentum. A large bus moving slowly and a small movement moving very fast can have the same momentum. Well, here's an example where impulse is the same, yet the outcome appears different. Alright guys, so we're going to implement dealing with impulse and momentum when we meet tomorrow, and we'll get into some graphical analysis of impulse as well. Until next time, physicists, until next time.